we can see your screen. Thank you.
Okay, just. Okay, so it gives me immense pleasure to join all of you in this forum on the 7th International Conference of Computer Science, Engineering and Technology. So my name is Waleed and I'm joining you from Doha, Qatar, and I'll be presenting the work that we did as part of our term project in a course of design and analysis of algorithms. And I'll be speaking on evaluating the impact of different types of crossovers and selection methods on the convergence of zero on Knapsack using a genetic algorithm. So I'd like to, with deep gratitude, I would like to mention our co-authors, Mr. Iyad Alexander and Dr. Mohammed Saleh, and we are from Department of Computer Science, Qatar University. And my name is Waleed, and I'll be presenting this work on the behalf of our team. So this is how we'll go about in this presentation. First, a brief introduction and providing a deep insight into the technical terms used in the genetic algorithm. Then some of the background and related work that has been done hitherto in the convergence using different crossover and selection techniques. Then a brief introduction and general insight into how a genetic algorithm actually works and the various selection and crossover methods that we have used in this experimentation. And finally, we discuss the results that we got, and then we conclude. So a brief introduction, what a genetic algorithm is. All of you know, those who are aware how what a genetic algorithm is. It's just a metaheuristic or an optimization algorithm, which does not give you the actual solution, but rather it gives you the nearest optimal solution. This is what the intuition behind the genetic algorithm is. And the basic reason why genetic algorithms were chipped in, because the gradient-based method was subjected to a lot of failure because it had the proclivity to get stuck in local optima. So that is the reason why genetic algorithms had to be chipped in. And the basic intuition behind this is that it is motivated by Darwinian natural selection. As you know, it's a biological algorithm, wherein the basic intuition is that as the generations progress, so does the fitness of your generation increase. So like what the Darwinian natural selection is, that initially how people evolved from an animal to a human. So the same intuition has been used in soft computing, and the basic general idea is that as generations progress, so does the fitness of your population increase. So why genetic algorithms were chipped in is because, you know, using an exhaustive search, which we also know call as brute force searching, even if today, you know, as you know how computational capabilities of supercomputers have increased, but still, if you use the exhaustive search, it is really computationally expensive. So that is why genetic algorithms had to be chipped in. That is why we use a lot of NP complete or NP hard problems. We use genetic algorithms because they give you a near optimal solution and they are less computationally expensive. And now a brief insight about the technical terms that we'll be discussing later in the presentation. So just to give you a brief holistic overview, initial population. So it just think of initial population as a set of chromosomes. So you have a set of genes of an individual, and each chromosome is a string. It's nothing. It's just a string of ones and zeros. So when we use a genetic algorithm in soft computing, your initial population is just a matrix of different chromosomes. And what our chromosome is, it's nothing, just a string of ones and zeros that represent your problem in a computational space. Then we have the fitness function. Fitness function is a mathematical function which determines how fit or unfit your chromosome is. Because if you remember what I said in the introductory part, that the intuition behind genetic algorithm is that as you progress in generations, so should the fitness of your population increase. And this fitness function, a mathematical function, gives us that score, the fitness score that we call in genetic algorithm. Crossover, the basic intuition is crossover that happens in a biological world, you know, when parents mate and offsprings are produced. Same happens in a computational space. Different chromosomes, they combine with each other and they exchange genetic information, or they exchange data. That you'll see how it happens. And then we have the mutation. Remember I told you that gradient-based method is prone to fail. Why? because in a big search space, it gets stuck in a local optima. So to introduce variation in our search space, we mutate some of the genes. We'll be seeing how that mutation happens. We mutate some of the genes, and that is the reason it, in a search exploratory problem, it doesn't let your optima to get at local optima. Rather, it lets it search the entire search space so that it can find the global optima. And this is just the graphical representation that I was telling you. So this entire matrix can be referred to as a population. One of the row is the chromosome, and as you can see, a chromosome is nothing but a string of ones and zeros that represent your problem space, and each chromosome has a value based on what your space is. Now, what we are going to do in this, so we'll be using genetic algorithm to solve a NP-complete problem, which is a 0-1 knapsack NP-complete, which you know as a non-deterministic polynomial algorithm. Okay, and the main idea behind 0-1 knapsack is that you got to fill a knapsack. Okay, it's a metaphorical knapsack. So your main idea is that you got to maximize the profit without exceeding the knapsack capacity. So in real world, you can think of it as, for example, if you're in a company and you have a budget and you want to maximize how you can use that money without exceeding, how you can use that limited or constrained budget, and you want to maximize the profit. So in 0-1 knapsack, we refer to it as that you have to reach your maximum profit without increasing the knapsack capacity. So knapsack metaphorically is just a sack, and if you exceed the weight, it will snap. Okay, so as I said, it is used in where you have financial constraints. This is just a mathematical representation of what a 0-1 knapsack looks like. You have items from 1 to n, each has a value and weight, and then we choose values based on their values, and the basic intuition, basic idea is that we want to maximize the profit based on their values, but we have two constraints. One, you should not exceed the knapsack capacity, which is this W. It should either be less than or equal to the knapsack capacity, because you don't want to overshoot the budget because you already have a predefined budget. As you know, the genetic algorithm is used in project scheduling or a lot of other things, project management and job scheduling. And there's another constraint, which is 0-1, and that is the reason why it's called a 0-1 knapsack. You can either choose an element or you cannot choose an element. So there is no condition where you can partially choose an element, as is the case in the general knapsack. But in 0-1 knapsack, as the name suggests, you either choose an element or you don't choose an element, which is characterized by 0 and 1 respectively. This is a brief, this slide gives you a brief insight as to what work has been done hitherto in this one. As you can see, some of the research, it has compared and contrast the results of genetic algorithm with greedy approach, branch and bound, and other algorithms. Some have compared various metaheuristic techniques to solve the knapsack problem. Others use the chaotic crossover method. Some of the research that used, they just had the main focus was towards various crossover techniques that were used in solving genetic algorithm, and they compared and contrasted the various crossover techniques were juxtaposed among themselves. And in other research that I have mentioned here, various selection techniques have been used. So as you can see, with the general trend in genetic algorithm vis-a-vis 0-1 knapsack has been that either the researchers, they focus towards what particular crossover technique has an impact on the convergence or the optimal solution or selection methods. So to the best of our knowledge, no such research has been done hitherto, which evaluates what happens if this crossover technique and this selection technique is mixed, and what is the impact of different combination of crossover and selection methods. So this is what we will be doing today. So a brief introduction of how a genetic algorithm works. So you generate an initial population randomly. This is just an initial population, as I remember the graphical representation that I just showed you in the slides before, aforementioned. So it's just a matrix of zeros and ones that you generate randomly. And then you calculate the fitness score by the fitness function that I've already showed how. And then we select the fittest individuals, because the basic intuition is that we progress in generations based on how fit or unfit the individuals are. And based on that selection method, we let the parents combine, or we let the parents mate, and then offsprings are produced. And then we apply mutation. Why? Because I told you to give variation in our search space so that it does not get stuck at local optima. And then this is a iterative process, and we go back to step 2 unless and until the termination condition is satisfied. Excuse me. Now, speaking about the termination conditions, there are 2 termination conditions in genetic algorithm. One is if you have a certain, if it's an exploratory search problem, and if you're searching for a particular thing, then when your search algorithm finds that optimum solution, it exits, or you have because in each genetic algorithm you have different generations. So if the number of generations is preset, then your genetic algorithm will stop when the particular number of generation is reached. So selection, the basic intuition behind selection is that we select the fittest individuals based on the fitness score, and what it does, it ensures that only healthy individuals are promoted to the next generation. So it's just a filtering process. So because the random generation, the random first generation is generated randomly, you don't want to take the unfit individuals based on the fitness score. So we just filter and we move ahead. So there are there are 3 types of selection methods that we have used in our experimentation that we'll be discussing. First is the rank selection. As the name suggests, each chromosome in a population is assigned a fitness score based on the fitness mathematical function that we have. And based on the fitness function, it is assigned a rank. So more fit your individual is, the higher the rank it will get. And then based on that rank, each individual has a probability of getting selected, which is given by this formula. As you can see, the probability is directly proportional to rank. So higher the rank, higher will be the probability of that particular chromosome to get selected. Second is the roulette wheel selection, also known as fitness proportionate selection. So after you have a chromosome and you assign a fitness score to it, and then based on the basic intuition is that the roulette wheel. So for example, consider this roulette wheel that is here. So suppose this this blue chunk represents a fitness score, which is the highest. So when you rotate the roulette wheel, the probability of this chromosome, which has the fitness function that is denoted by this blue area. So it has the higher probability of getting selected because it's directly proportional to the fitness score. So this is another selection method that we have used. And the third selection method is the tournament selection. Basic intuition is how matches are scheduled in soccer matches or cricket matches. The basic intuition is that various chromosomes compete with each other, and this process, the pooling system that happens in mostly the cricket and football matches, the 2 teams compete with each other, and this process happens so on and so forth, unless and until we get the match winner or the fittest individual. So basic intuition is just what happens in sports games. Now the crossover methods that we have used, crossover, as you know, takes its intuition from the biological algorithm that parents mate and offsprings are produced. And technically there are 2 types of crossover methods that we have used. One is the single point crossover and 2-point crossover. Let's have a brief look at what these are. So when you have, in this diagram, as you can see, you have 2 parents, right? Each parent has data. And then as a single point crossover, as the name suggests, you just have 1-point crossover that you determine in the algorithm. It is predetermined. For example, in this one, you have the 8th point set as crossover method. So 2 parents mate, they have the particular crossover point, and what happens? The genes get exchanged. As you can see, a string of 3 ones and a string of 3 zeros, they get interchanged inter alia, and this is how mating takes place in genetic algorithm with vis-a-vis soft computing. And then we have the 2-point crossover. As the name suggests, there would be 2 points of crossing over the data with 2 parents. So you have 2 parents mating with each other, and you have the 2nd and the 7th point as crossover point. And what happens after mating? The data gets exchanged at the 2nd and the 7th point. As you can see, the data is exchanged between the 2 strings. Now we get to the most important and the interesting part, is the results. So now I've already told you the 3 selection methods that I've used and the 2 crossover methods we have used. So we had the 0-1 knapsack, which had the following weight. As you know, a knapsack, 0-1 knapsack is characterized by 3 things: weight value and the knapsack threshold. So you have 17 items in your knapsack, and your profit cannot exceed 29, okay? And in the testing environment that we had, these parameters were kept constant. That is the number of generations. That means that your algorithm will terminate when the number of generations reach 50. we have another parameter which is known as solutions per population. Solutions per population is nothing but it is just your when your initial first, remember the first step in a genetic algorithm is that a random initial population is generated. Now you need to know, you need to tell your algorithm, you need to tell your program as to how many chromosomes will be in the first generation. So 8 chromosomes will be there. Now mutation rate was kept constant in the entire testing process, and the mutation rate 0.4 means that after crossover happens, each chromosome, the final fittest chromosome that we have, each chromosome has a probability of 40% that it will be mutated. And there are different types of mutations in genetic algorithms, but we kept it constant at bit flip mutation. Why? Because we didn't want our testing environment to change. We wanted it, because all these 4 parameters are constant, so we want to use them as baseline, okay? Now, the type of mutation, as I said, there are a lot of type of mutations in genetic algorithm, but we use the bit flip mutation. As the name suggests, in bit flip mutation, what happens is that any random bit with a probability of 40% gets inversed. So if the data at that, for example, let's just say at the third, your genetic algorithm determines that it wants to inverse the third bit. So if the third bit was 1, it will inverse it to 0. If it was 0, then vice versa. And what it does, already told you, it gives you our search space more variation. And these are the properties of the workstation that on this the experiment was done. The algorithm was written in Python 3.7. I think it was probably 6 months before, because 3.7 was the latest by then, and it was written in the PyDev module of the Eclipse IDE. Now, here are the results of scenario 1. So in scenario 1, what we did, we combined 1 point crossover with rank selection. So crossover method used was 1 point, and the selection method used was rank. So as you can see in the figure, the results show a spike towards the optimal solution from the 15th generation. So in the 15th generation, it is increasing, but there's a sudden spike at the 15th generation where it suddenly spikes to the optimal solution, and then at the 17th or 16th generation, it gives you the optimal solution of 52 for the 0-1 knapsack. Then we go to the scenario 2. So as you can see, it's quite slow, because it is first the fitness is increasing, then it is decreasing, then increasing, and then it gets stuck at, as you can see, it gets stuck at the fitness score of 43 for about more than 20 generations, where it suddenly spikes to 50. So as you can see, the optimal solution for the 0-1 knapsack that we considered is 52, but this combination does not give us the optimal solution, because at the end of the 50 generation, the optimal solution that it gives to you is 50 and not 52 as it was supposed to give. Now, what we have the scenario 3. So scenario 3, the crossover method used was 1 point crossover, and the selection method was tournament selection. Now, what happened in this one, as you can see, in the first generation itself, it gave you the optimal solution, okay? So neither it increased nor it showed a decrease, but just one initial population was generated, and when it converged the second generation, it just gave you, starting, as you can see, from the first generation itself, it is giving you the optimal solution. Okay. By the way, this is just an individual representation. We'll compare and contrast it in later slides. Okay. Now, scenario 4. As you can see, scenario 4 is a combination of 2 point crossover. The crossover method is 2 point, and the selection is rank selection. So as you can see, it is stuck at local optima of 40 for about 8 generations. Okay, and then it shows a sudden spike to 48 in the 10th generation. And then finally, it does converge to the optimal solution in I think the 15th or 16th generation that we'll be seeing in the compare and contrast table. So the penultimate scenario 5 is a combination of 2 point crossover with the roulette selection method. So because we have 3 selection methods and 2 crossover methods, so this entire search space is 3 cross 2, which is 6. So we have around about 6 scenarios. So as you can see, in this scenario, as you would have probably guessed, it is worst scenario that we just have seen hitherto. Your optimal solution starts at 45. Okay. Now, despite, on the contrary of it increasing its fitness, it's showing a sudden decrease. It dips to 39, and then it suddenly spikes to the same optimal solution of 45. So the standard deviation from the optimal mean is very large. Okay, in the negative, if you go to the left side of the mean. So 45, it's converging to 45, does not give you the optimal solution, okay? Now the last scenario is the combination of 2-point crossover with tournament selection, okay? So as you can see, it converged to 52 at the beginning of the 20th generation, okay? Now, we have a compare and contrast table for all the 6 scenarios. So the generations, as you can see, remained constant at 50, okay? Now the best value that we got in scenario 1 was 52. In scenario 2, we saw it was 50. Scenario 3, 52. 52 in scenario 4 and 45, remember, our algorithm converged to 45, and scenario 6 was 52 as well. So this is just the mean and standard deviation from the mean of the entire optimal solution. So did it give the optimal value? Only scenario 1, scenario 3, scenario 4, and scenario 6 gave us the optimal. And this row shows us generation at which optimal value was given. So scenario 1 gave the optimal value at 17. Scenario 2 did not give an optimal value, so just not considered. Scenario 3, remember, in the first generation itself, it gave us the optimal solution. Scenario 4 in the 14th generation. Scenario 5 is not applicable because it did not converge, so we just filtered it out. Scenario 6 gave in the 13th generation. Now the maximum weight, remember, the knapsack capacity was 29, so all the algorithms gave you a maximum profit of 28. So that was constant throughout. Now here's the thing, and if some of you would have worked in algorithms, you know that whether an algorithm is deterministic or non-deterministic, every algorithm has a space complexity and time complexity. But as we progress in research, we do not care more about the space complexity because space nowadays is not a constraint. But although time complexity will always remain the focus of research, but in genetic algorithm, although most of the evolutionary algorithms, they do have time complexity, a basic standard criteria that this is the algorithm and this is the time complexity formula. But in genetic algorithm, unfortunately, there are different schools of thought, and I mean the research has been going on since forever now, and still it is a subject, it's a subject of contention between researchers. There's not one particular formula that gives you that there is no predetermined formula that this is the time complexity. But given what is the trend in the research nowadays, although there are there's a lot of contention between researchers, but most of the researchers, they agree that the time complexity of GA depends on a number of factors, and one of the factors is the number of generations. So we can infer based on that what the researchers are hypothesizing, that if you reduce the number of generations, so does your time complexity decrease. So this is the intuition that what we concluded on. We said that in scenario which is a combination of in scenario 3, as you can see, which is a combination of 1-point crossover with tournament selection. So we say that combination of 1-point crossover with this tournament selection gives you the less time complexity. Why? Because the number of generation is less. So this is just a discussion of what we just discussed in the previous slide. So 50 generation was used as baseline. Okay, so only two scenarios failed to converge, but we concluded that the convergence rate of combination of 1-point crossover with tournament selection with respect to 0 and knapsack that we consider is highest. Why? Because the number of generations is less, and thus we conclude that this scenario and that means this crossover method and this tournament selection is the most efficient in solving 0 and knapsack, and that would reduce the time complexity. Now, a lot of future considerations. One, it would be interesting to combine genetic algorithms with other metaheuristic algorithms and gauge the impact. Another limitation of this, prototype is that our search space is small, but we would like to, explore, huge search spaces and to see what will be the impact of this algorithm that we implemented on that, prodigious search space. Another possible future work would be evaluating the impact of different types of mutation. Remember, I said that in the testing environment, we kept the mutation fixed as a baseline because we don't want to change the testing environment, but there are different types of mutation, and we would like to see what will be the impact on convergence. Then the scenarios will be 3, then we'll have a different crossover method, we'll have a different mutation method, and we'll have a different selection method, and we'd like to see what is the impact and how whether it increases time complexity or whether it decreases time complexity. These are the references that we used in this work. And yeah, that would be it from me. Thank you. If you have any questions, please feel free to answer. This is my profile on LinkedIn. If some of you would want to join me there, I'm a master student at Qatar University. And yeah, that is it. Thank you so much for your time.
Thank you, Mr. Walid. The presentation is very good. You did a wonderful job, mate.
So if you have any questions, please feel free to ask. I'd love to answer your questions.
Is there any questions from forum? You can unmute your microphone and you can ask. If you don't mind, Mr. Walid, apart from Python, did you use any software or any tool to do the experiments?
No, we implemented the genetic because we created our own. I mean, the algorithm is there, the framework is there, but we did not use any other framework. We implemented this, framework from scratch, and it was done. But it's a good idea. I mean, compare different, executing environments, and we can see the impact on it. But as for this one, the constant, one of the constants that you did mention is that we only used one testing environment and in only one framework, which is the Python implementation, and not. Although there are other tools, wherein you can just feed the data and you get the. But I don't think that reliable, or you can see. But it will be a good idea to compare and contrast with when you implement the algorithm yourself, or when you see the different types of tools that are available, wherein you give the genetic algorithm converges. So yeah.
Thank you very much, Mr. Walid.
Please, I have a question, please.
Yeah.
Why do you choose genetic algorithm?
Why do you choose the genetic algorithm?
Yeah, if you would remember, I said in the second slide itself that there are different types of methods that have been used to solve NP-complete or NP-hard problems. Because if you just go by the random brute force, the computational time, it's it's an order of the computational time complexity is big O of order of n square or even nn. But it has been proved, and research hitherto shows that the use of evolutionary algorithms like genetic algorithm, or you have particle swarm optimization, or you have there are different types of evolutionary algorithms. You have particle swarm optimization, you have bee colony, you have ant optimization. The research hitherto shows that if you solve NP-hard or NP-complete problems using evolutionary algorithms, the time complexity decreases as compared to the other, deterministic polynomial algorithms. So that was the basic intuition of using genetic algorithm in solving zero knapsack.